We are currently studying the singleton pattern. As you've seen in how to create and instantiate a singleton, there is a lot of work involved and there are a lot of subtleties. One of those important subtleties are synchronizing the access to create a singleton to ensure that exactly one of that object is instantiated. Since synchronization forms such a core part of using and setting up singletons, let's take a small segue and learn about synchronization in some depth. That's what this particular class will be about. Let's talk about synchronization and the issues that can crop up while using multiple threads in Java. If you think about old school threading support in Java, the threads normally communicated with each other via shared objects or shared member variables within the same object. That was a very standard way of threads communicating. They had the same memory space, so they'd access the same memory space in order to pass messages to each other or pass results to one another. Now, three types of complications can arise from this type of communication, where multiple threads can access the same piece of memory. Let's look at what they are. The first is thread interference. The second is memory consistency errors. And the third is thread contention. These are the three kinds of errors that occur when multiple threads are allowed to access the same piece of memory. So when do we have thread interference? When different threads access the same data at the same time, they can interfere with one another. Now there's no problem if they're just reading that data, but what if they were writing it? This means that the order in which the threads write the data determines the final outcome of what is stored in that memory. And it may not be the outcome that you actually want. So, threads interfere with each other can produce different outcomes when they access the same piece of data to write to it. So, what are memory consistency errors? Say we have two threads running, thread 1 and thread 2, and thread 1 goes in and updates some variable in memory, and thread 2 wants to consume that variable which thread 1 has updated. It's totally possible that thread 2 sees a stale value of that variable. Maybe thread 1 hasn't finished updating it yet. These kind of issues are very common when multiple threads use each other's value and pass this information via shared memory. The third complication that can arise in multi-threaded programs is that of thread contention. This happens when two or more threads constantly get in each other's way. This basically ends up with none of the threads making any progress towards completion, and it's totally possible that one of these threads might have to be killed by Java. This is a state you don't want to get into. All threads are supposed to help make progress by making things faster and in parallel. But if they contend with each other, that's not going to happen. So that's another complication that can arise with multiple threads. Let's look at thread interference and memory consistency errors in a little more detail. If two threads access the same variable, it's possible for them to get in each other's way and interfere with each other's operations. Why is that? This is because Java, when working with multiple threads, allows switching in and switching out of threads midway between their executions. So Java might switch execution from one thread to another, even halfway through a seemingly simple atomic operation. Consider a very simple operation like incrementing the value of an integer in memory. So like an I++ operation. This is actually 3 bits of code. You'll read the value, increment it, and write it back. It seems like an atomic operation, but it really isn't. So if you have two threads incrementing the same variable, it's totally possible that the increment that one thread has done is just lost. So say thread A comes in, it has read the value of a variable, it increments it, but before it writes it out into memory, Java has switched out thread A and switched in thread B. This means thread B will read the same value and then increment it. And then let's say thread A comes in now, it will write out one value. And thread B's increment will just be lost. Thread B operated on stale data, we lost the information. So what's the solution? The solution in such cases is to make sure that a section of code which you want to be atomic, which you want a thread to complete in one go, should be accessed by only one thread at a time. Now, restricting access to an object or a variable, which is locking the variable so that only one thread can access it at a time, is a very, very powerful concept in computer science. It's very widely used, especially in databases. We want to make sure that database updates are consistent and atomic, and multiple writes do not interfere with one another. We use locking in databases. Similarly, we can lock sections of code which access the same portion in memory. The solution to thread interference and memory consistency errors is basically locking. Locking variables correctly can eliminate these errors from your code. However, obviously, if you gain something, there is a trade-off that you need to make. And the trade-off while using locking in order to eliminate these threading errors is performance slowdown. Using locking slows down performance and can lead to thread contention. So basically, you eliminated two issues, but you've made one issue worse. So if you remember, the three issues were thread interference, memory consistency, and thread contention. By eliminating the first two using locking, you made thread contention worse. We'll see how that works. Thread contention can be due to starvation, live locks, or deadlocks. We'll go into the details of what these mean. However, all three of these conditions effectively mean that a particular thread can no longer make progress. Now, locking of a variable is done in Java using the synchronized keyword. Let's look at the synchronized keyword. Now, it's important for us to know that every object in Java, no matter what class it is, or whether it's one of the regular objects like integers, strings, which are predefined by Java, all of these objects has a lock associated with it. Every object. This lock that is associated with every object is called the intrinsic lock or the monitor. What is a lock? A lock is a way by which we can restrict access. If you in the real world, if you have a lock on the door, effectively you're restricting access to what's behind the door to only holders of the key for that particular lock. It's the same analogy in code, and if you keep that in mind, locking will be easier to understand. Now, under normal circumstances, this lock is always open, which means any number of threads, and if you imagine that people entering the room are actually threads, so any number of threads can access the object at the same time. So when the lock is open, any number of people can go through the door and enter the room at the same time. There is no restriction. This is the normal way Java functions when you don't use locks or when you don't use the synchronized keyword, which is the basis of locking. So that's easy to imagine. However, it's totally possible to specify that a thread can only execute a section of code once it has acquired the lock on some object. So if you go back to our locked room analogy, you can always lock the room where the room is the section of code that you want to execute and the lock is the object. So you can say that only when a thread has a lock on a specific object, can it execute a particular section of code. So only when a person has a lock on that door, has a key to the lock on that door, can he enter through and go to the room. Now, if some other thread holds that lock at any moment in time, the current thread needs to wait its turn. This means some other person has entered the room and closed the door on you, and you don't have the key to the lock to enter, so you need to wait your turn. It's exactly the same in threading. This ability to give a lock to only one thread for any section of code is achieved using the synchronized keyword. The synchronized keyword is what you use to kind of activate the lock or the intrinsic lock on any object. And this lock on any object can be used to restrict access to a section of code. This will be clearer as we move on with threading, but it's important to get this concept exactly right.